Good day, everyone, and we meet yet again. And so we are just concluding on our stoichiometry section, okay? But what I wanted to do is just to extend once again. People always struggle with those 8-mark questions on acids and bases. And I just wanted to show you how the understanding of stoichiometry can actually help us in those examples. So I'm going to take a very difficult example, but if you follow on in what I do, you should be able to get this quite well. Okay, so if you haven't subscribed to our channel, please do the right thing. Okay, and please just put a thumbs up if you like the content, and you are more than welcome to tell even more people about the channel as well. Okay, if you are benefiting from it, I'm sure it will benefit others. Okay, right, now let's get into the question. So we've got an example here. All right, they say an impure sample of magnesium with a mass of 0.45 grams, so reacts with 200 cubic centimeters of a 0.2 moles per cubic decimeter nitric acid solution. Now, just like we did in our previous video on stoichiometry, you'll notice what we did there is that we had an impure sample, all right? And what was the issue with an impure sample is that as much as we're given that mass there, you couldn't use that mass because that mass, it will not react completely. Not all of it is actually made of the actual substance, okay? So in that reaction there between magnesium and nitric acid, you actually don't have the mass of the magnesium. Why? Because that 0.45 is the mass of the impure, which means it's the magnesium with the other stuff. Okay, right. So I hope that you get that. Right. So it reacts with the nitric acid. Okay, there we're given the volume of the nitric acid as well as the concentration of it. Okay, they say to us the acid is in excess. So what does that mean? It means during the reaction, we took magnesium, we put some nitric acid into it, and as a result, so what actually happened is that there'll be some of the acid that remains unused. It's in excess, so there'll be an amount of acid that remains in excess, unused, right? So now, or unreacted if we want to look at it that way. So they say now the acid that remains is neutralized. So that it means the acid that we were left with from this reaction, okay, we are now going to use in another reaction. Okay, so in this case they say it's remains, okay, it's neutralized. Okay, 35 cubic centimeters of 0.2 sodium hydroxide. So we react the remaining acid, and remember, we don't know how much of it is there, right? We are going to react it with sodium hydroxide, okay? And what we actually want to work towards is just work our way backwards there. Now, ladies and gents, I want you to please follow on in what I'm going to do, okay? So our problem here, we want to find out about this guy. We want to find out, they say, calculate the percentage purity of the magnesium sample. So essentially, I want to work my way backwards so that I find the mass of magnesium, the actual mass of magnesium. Okay? So where do I begin? I'm just going to say, well, first of all, it means that I need to find out how much nitric acid reacted. Why do I want to do that? If I can find out how much acid reacted, therefore it will help me using my stoichiometric ratios. I can be able to determine the amount of magnesium that reacted alongside with it. Okay? I hope you can follow that. You can follow my logic, right? So if I can find out the amount of nitric acid that reacted, then I can be able to find out the amount of magnesium that actually reacted with it. Okay, so now what do I have on nitric acid? Well, they first of all tell me the amount that I started with, okay, of nitric acid. So if you don't mind, what I'm going to do, let's find out from this amount how much nitric acid do we actually have. So we're given the concentration as well as the volume. So you know how to convert from concentration to volume, right? Okay, sorry about that. So we know how to convert from concentration to volume, right? Okay, so let's find out first of all how much nitric acid did we originally have. So I'm going to say, well, let's find the number of moles, okay, the total number of moles. I'm trying to actually create some space over here. Okay, so number of moles. So we're going to use our concentration formula, right? So number of moles is concentration multiplied by the volume. So remember, this comes from concentration is number of moles over volume, right? I'm sure you know this by now. So our concentration value, that's 0.2, multiplied by the volume. Please remember that we said our volume has to be in cubic decimeters. I'm sure you know it by now. Okay, how do we convert that from cubic centimeters to cubic decimeters? We divide that by 1,000. So 200 divided by 1,000 gives us 0.2. Okay, I'm not going to waste time on that. Okay, so that's 0.04 moles. Now, what are these? These are the number of moles of nitric acid, okay? But these are the number of moles that you have in total. So those are not the number of moles that actually reacted with the magnesium. Okay, so those are the number of moles that you have in total. Okay, I hope that makes sense, right? So those are the total number of moles of nitric acid. So is it possible for me to find out how many did not react? Remember that we took those number of moles, but not all of them actually reacted during that reaction. There's an amount of nitric acid that was in excess that remained, and what we did was to find that number that remained, and we used it in the previous in the next reaction. So what I'm going to do is, let's go now into the next reaction where nitric acid reacted with sodium hydroxide. And what do? Deliberately they give me more information about sodium hydroxide. Now I want you to please note, we took an amount of nitric acid, so if you imagine, so there we had it, there's an amount of nitric acid there, okay, and we used it with magnesium, okay, so it reacts, there's a magnesium chunk there, we put some of it there, but there's an amount of nitric acid that still remains unused, okay. So that nitric acid that remains unused, we are now going to say, okay, you are going to react with someone else there, and that is going to be the sodium hydroxide, okay. But what they do is they tell you about sodium hydroxide, they tell you the concentration of it, 0.2, okay, but they also tell you the volume that you use, okay, cubic centimeters, okay. So now let's find out how much of the nitric acid actually reacted with the sodium hydroxide, okay. So I'm going to use, by the way, you can use from acids and bases, okay, CAVA over CBVB is equals to Na over Nb. Now, remember, this is an acid-base reaction, okay? So I'm saying I know the concentration and the volume of my base, sodium hydroxide. I know the concentration of the acid. Where do I know the concentration of the acid from? It was given to me initially, right? So I know the concentration of the acid, okay? So I'm going to just substitute there. Okay, so concentration of the acid, that's going to be 0.2 multiplied by the volume of the acid. So that's what I would not know. I don't know how much was left after it reacted with the magnesium, and as a result, I don't know how much of it reacted with the sodium hydroxide. So I don't know what the volume of the acid is. Okay, there's another approach to this if you're not following on here. Right, so 0.2 multiplied by the volume of the acid, but the concentration of the base, again, they told me it's 0.2, there it is there, multiplied by the volume of the base. Okay, and the volume of the base is 35. Okay, and this is equals to the number of moles of the acid. Okay, for those of you who've watched acids and bases, I said when we are titrating, all we focus on is that those stoichiometric ratios there. So that's going to be 1/1. Okay, so in this case, I can simply find the volume of the acid, and the volume would exactly be the same. You cross multiply there and you'll get 35 cubic centimeters. Okay, in fact, if you ask me, probably I'm just complicating this a little bit. In fact, let me go back to stoichiometry. Okay, so you've got the concentration of the acid as well as the base, as well as the volume. So can we not get the number of moles of sodium hydroxide? Of course we can. All right. For those of you who haven't watched acids and bases, you can forget about this a little bit, okay? But obviously when you watch that video, you'll understand why I use that one. So we can find out what are the number of moles of sodium hydroxide, okay? I want us just remain consistent with using stoichiometry. So number of moles of sodium hydroxide, that's concentration times volume. This is going to be 0.2. Remember, our volume must be in cubic decimeters, right? So you'll say 35 divided by 1,000. So that's going to be 0.035, okay? And what does that give us? So that's 0.035, okay, times 0.2, okay? And you get 0.007. So that's 0.007, and note that is in moles. So those are the number of moles of sodium hydroxide, okay, that reacted there. But remember, we also know our molecular ratios, right? Our molar ratios. It says for every one that you use of sodium hydroxide, you'll use one of that. So to keep consistent, it means for every one sodium hydroxide that I use, I will use one nitric acid, 1 mole of nitric acid, HNO3, right? So again, I want to know if I use 0.07 of sodium hydroxide, how much acid am I going to use? I'm sure you can see this by now, ladies and gents, that it will be the same amount, right? For everyone, there's 1. For 10, there's 10. So it means for 0.07, there'll be 0.07. But you can also use stoichiometry, and that will give us 0.007 moles. Okay? So now what are these? These are the number of moles of nitric acid that reacted in that reaction. But keep in mind, these are the amount, or this is the amount of nitric acid that was in excess in that previous reaction. Okay, so remember, we reacted the nitric acid, some of it was left, and whatever was left, we reacted in that reaction. So this is the excess amount of nitric acid, 0.007 moles. Now I want you to follow me carefully, ladies and gents. So how much nitric acid actually reacted there? Now note, so the number of moles of nitric acid that actually reacted in that reaction will be the difference between the total amount that we started with, subtract the one that was in excess. Think about it. Whatever I used here of the nitric acid would be the difference between what I had in total and what I had in excess. So whatever I had in excess, it's minus whatever I actually used there. I hope that makes sense, ladies and gents, right? So the number of moles that reacted will be the total amount of moles. Remember, I am actually using the same thing. It's nitric acid minus the amount of moles that were in excess. Okay, so in this case, I've got a total of 0.04. Okay, and in excess I had 0.007. Okay, so meaning that how many moles did I actually use? I actually used 0.033 moles of nitric acid. Okay, so it means 0.033 moles of nitric acid actually are the ones that reacted with the magnesium. I'm sure you can see this by now, ladies and gents. Can I now determine the amount of magnesium that reacted? Absolutely. I've got number of moles of that. I can now determine number of moles of magnesium, right? So I can say, please, if you don't mind, I'm just going to write it over here. I'm going to say, okay, for every 1 mole of magnesium, I actually use 2 moles of nitric acid. I keep writing it wrong there. 1HNO3, right? So for every 1 mole of magnesium, I use 2 moles of nitric acid. So I want to know how many moles of magnesium, right, will I require in order to use 0.033 moles of nitric acid. Okay, I hope you're following, ladies and gents. So this simply says to me, okay, now I can cross multiply. 2 multiplied by x, that's 2x. Please, if you don't understand, it means that you simply have not watched my previous videos on stoichiometry. Please make it a point that you do that, ladies and gents, right? They will help you quite a lot. So 2 multiplied by x, that will be 2x. 1 multiplied by 0.03, that will be 0.033. Okay, and we divide both sides by 2. And in this case, what do we get? I'm just going to write it onto this side. Okay, so it means that my x value, right, so that's 0.033, you divide that by 2 and you get 0.0165. So 0.0165 moles. Now, ladies and gents, please, I want you to follow in what I'm saying, right? What are these moles over here? Remember, what we wanted was this x over there, right? What does the x represent? It represented the number of moles of magnesium that reacted. And remember, the magnesium that reacted would be the pure magnesium, isn't it? Okay, so this is the number of moles of pure magnesium that actually reacted. All right, so now can I get the mass? All right, let me just write it as number of moles there, if you don't mind. So the number of moles of magnesium. Okay, is it possible for me therefore to get, or rather to determine, right, the mass of the magnesium? Okay, remember, I've got the total mass of the impure sample, but now I want the pure sample, or the pure amount of magnesium. So all I'm just simply going to say is number of moles, that's mass divided by the molar mass. Okay, so I already have number of moles of magnesium. Okay, so that's 0.0165. okay, sorry for that clumsiness over there. Right, so that's 0.0165. I want the mass. And what's my molar mass for magnesium? Okay, of course you would know by now. We go to our periodic table. Magnesium has a molar mass of 24. Okay, right, so in this case we're going to say, okay, that's 24. So we multiply that. Okay, we cross multiply there. Okay, and what we do, right, so I get a value of 0.396. okay, So that's 0.396. So therefore, okay, please let me just make right. So therefore, it means the mass of pure aluminium is 0.396 grams. Okay, right. Remember, what did they want us to determine? The percentage purity. I'm sure you can see it by now, ladies and gents, right? So now how do I determine the percentage purity? Okay, from our previous videos, I showed you how to do that. Okay, all I'm simply going to do, I'm going to take the mass of the pure substance. I'm going to divide that by the mass of the impure sample, right? Okay, so this is going to be 0.396. Remember, because we're dealing with a percentage, we need to multiply that by 100, right? So 0.396 divided by our mass there was 0.45. So that's 0.45 grams, okay? And we multiply that by 100. And I'm sure you should be able to get the answer quite comfortably. Divide by 0.45, and I get 88%. Okay, so I get a purity of 88%. Okay, right. These are, by the way, called back titration. This is called back titration. Okay, and you'll find these quite a lot. For those of you who are doing analytical chemistry, these are the typical examples that you find quite a bit. Okay, and for those of you who are doing metric and doing acids and bases, please try to understand these are usually worth about 8 marks or so, and I'm telling you, once you understand what I've done here, you will be able to follow on and go on to get those 8 marks. All the best as you prepare for your exam. Otherwise, from me for now, it's goodbye and sharp.